Welcome to Maths with EJD. I've been making videos on basic calculus, and today I continue in that same area. And today our focus shifts to differentiation. Starting from this video, in the next 4 or 5 videos, I'll be focusing on different aspects of differentiation as we look at techniques of differentiation. But first of all, we need to understand what that is all about. Okay, like this is a synopsis of what this module 3 will be about, which will be in about 4 or 5 videos. Of course, we see the introduction. We'll look at differentiation from first principle. So the first video will be about introduction and differentiation from first principle. That's the first video on that differentiation. Then the next one will be on differentiation of polynomial functions and function of a function, which is also known as chain rule. Then another video will be on product rule and quotient rule. And then, okay, a fourth video will be on implicit functions, logarithmic functions, exponential functions, and parametric functions. And then, of course, you have exercise to go with each one. So this is the module 3. And before I made 4 videos, 2 on functions of real variables, another 2 on limits and continuity. So on differentiation, we'll be having 4. So it means that video 5, 6, 7, and 8 in the differentiation, in the basic calculus playlist will be about differentiation. So let's move on. Okay, so what when you hear about differentiation, what actually comes to your mind? A very good example I can give you is, back in secondary school, right? Probably during your physics practicals or something, you would take readings with equipment, and then at the end of the day, you're expected to plot graphs. And then your graphs, uh, especially if you're plotting straight line graphs, right? Your graphs can be of 2 forms. It can be upward sloping, like what we have in this figure, or it can be downward sloping, like this one. So in the first one, right, you see you have x1, x2, but then at x1, so the x1 corresponds with y1 and x2 corresponds with y2. So you see that the values of y is increasing as x is increasing. But in the other case, now you see that the value of y is increasing as the value of y is decreasing as x is increasing. So because at x1 now, at the initial point, the function is there, but at x2 now, the function has reduced here. So, and at the end of the day, everything comes down to slope. This one is sloping upwards from left to right, and this one is sloping downwards from left to right. And that has a lot to do with differentiation. So here we simply have graphs with positive and negative slopes. So this is positive slope because it is sloping upwards, and then this is negative slope because it is sloping downwards. So let's see how that connects with what we have. No, take note of the x1, x2, y1, y2, and everything, and the whole idea of slope normally, which of course we must have learned in secondary school mathematics, or what some people call high school. Okay, so let's see the idea of slope now. Differentiation versus slope. Let's see how they connect. From the above figures, you see that slope generally is seen to be change in y over change in x. So if you look at it from the graph now, you see like change in y, this change in y divided by this change in x. Or if you want to look at it from the first one, this is like change in y over change in x. So that's the basic idea of slope. So change in y over change in x, and change in y means that you have y2 minus y1. You have y2 minus y1, that is change in y, over x2 minus x1, which is change in x. And in summary, you can write it as delta y over delta x. So you can see it's beginning to come up gradually. So the first figure has a positive slope representing positive change. The one sloping upwards represents positive change, while the second one has a negative slope, which represents negative change. So you see this has a positive slope, this has a negative slope, and that is positive change and then negative change. All right. So how do we then define differentiation in terms of this slope? Now, you discover that differentiation is about the relative change of the dependent variable. The dependent variable is y, with respect to the independent variable x. So the change in y over change in x. That's the basic idea of differentiation. As such, to differentiate a function is to find out whether it is changing positively or negatively. And then that takes us to the next slide. That should be slide 6. Um, this is slide 6 here. Okay. So, I mean, basically, like we have seen already, we can say that differentiation is all about looking for the change in y all over the change in x. And this, of course, has bearing on our daily lives. A very good example I like to use is the idea of the growth of a child. You know, when a child is born, right? The growth of the child is dependent on at least three things. It depends on genetics, maybe the genetics from the parents. The growth of the child also depends on nutrition, the kind of feeding the child gets, and then it also depends on maybe the environment in which the child grows, right? So, but in this case now we are dealing with just single valued functions. So let's just assume that growth depends on nutrition, for instance. Now, so in this case, the differentiation of this of g with respect to n would just be something like dg dn. That is the rate at which the child is growing with respect to the rate at which the nutrition the child is getting nutrients, basically. So that's the whole idea. So the rate at which the growth is changing with respect to the food the child is eating, or any other factor you may want to consider. So, and that takes us to the idea of differentiation from first principle. Now, the first principle of a thing is that is like the original way it was done. For instance, when the whole idea of mathematics started, right? At first, there was nothing like X and Y, you know. So it's just people talking normally, like, okay, like as I moved towards the market, I began to hear the noise, I mean the sound of music, some people playing drums louder and louder. That's basically the idea of limits, right? The closer you get to the market, the higher you begin, the higher the noise you hear of the people playing maybe drum in the marketplace or something like that. So that was how it all started. But over time, people discovered, oh, maybe it would be more convenient to represent these ideas in terms of symbols. And that's how we came about algebra, which has led to so many other things. Okay, so talking about differentiation from first principle, right? First principle differentiation is based on the fact that a change in delta x, which is the independent variable x, you know, the change in the independent variable is delta x. That change causes a corresponding change in delta y in the dependent variable y. And that you can represent as dy dx. And just like I told you, differentiation is impossible without limits. And that was why we had to learn about limits before we got here. So you discover that this your dy dx finally is actually the limit of delta y over delta x as delta x approaches 0. So differentiation is all about limits, just like you can see right now. So dy dx is the limit as delta x approaches 0 for delta y over delta x. Delta y is the change in in y, and delta x is the change in x. Of course, when we say change, it can be positive or negative, just like you've seen already. So let's see how the whole idea of differentiation came about from first principle. So you can appreciate when we begin to introduce other techniques. Now, given a function f of x, right? You have this function f of x. So it means you have y equals f of x. And we are saying, you already know that x is independent variable. So you can pick x randomly. But once you pick x randomly, you cannot pick y randomly because x automatically determines y. Okay? So y is f of x. And if there's a change in x, meaning that x is increased or decreased by a little value delta x, that automatically affects the value of y itself. So y also changes by delta, by a little, it has a little change, whether increase or decrease, and that is delta y. So in this case now, you see that instead of f of x, now I have f of x plus delta x because x has increased or decreased, and then that leads to a corresponding change in y. So you now have y plus delta y, which is maybe delta y, which is a little increase or a little decrease, as the case may be, depending on the function you're dealing with. And then, so if you look at, so from here now, you can transfer y to the other side. So you have this expression that delta y is f of x plus delta x minus y. And then you don't forget that y is actually f of x. So so you can put f of x in that place. So you have delta y equals f of x plus delta x minus f of x. And then if you choose to divide through by delta x, see what you get. You get delta y over delta x equals f of x plus delta x minus f of x divided by delta x. So at the end of the day, you see what you have here is actually delta y delta x. That's like a rough delta, a rough change, which still has some so-called impurities. But the way to remove that impurity is to take the limit, so to speak. So you have, if you now take the limit of delta y delta x as delta x approaches 0, then you get the refined differential, the refined dy dx. And then that refined dy dx is actually the same thing as the limit as delta x tends to 0 for f of x plus delta x minus f of x all over delta x. So so this now becomes the definition for differentiation by first principle. Okay, so based on that, let's take some examples. Normally, for those who already know how to differentiate, you can just write the answer in one blow. Once you see y equals x cubed minus 4x squared plus 7x minus 1. I think I gave some examples when I was talking about L'Hopital's rule. So this is simply delta y delta dy dx equals 3x squared, that short way, minus 8x plus 7. But if you do it like this, okay, plus 7, right? But doing it like this, you don't, it's very easy, just straightforward. But it wasn't that easy initially. So it came about through first principle, which I think it's important to get exposed to, so you can appreciate when you do it this easily and you get it, so you can appreciate where it all came from. So based on what had been established in previous slides, so we want to differentiate y equals x cubed minus 4x squared plus 7x minus 1 from first principle. So if you are doing in a theory question and you're given this, if you just differentiate it the way I've just done it, you'll be wrong, right? Because it is specified I should do it from first principle. First principle can be messy, lengthy, and annoying. But I mean, if you have that instruction, you have to do it that way. Okay, so how do you go? You start this way. You have y equals x cubed minus 4x squared plus 7x minus 1. And the basic idea of first principle is that an increase or decrease, which is overall a change in x, which is delta x, automatically leads to a change in y. So that means everywhere you have x, the x now increases. So if instead of x cubed, now you have x plus delta x cubed minus 4x squared, that's x plus delta x squared, plus 7x, that's x plus delta x minus 1. So as this is happening, this automatically affects y. So you have y plus delta y. So now that that is taken care of, the next thing is to expand all this. You expand this. So, and your knowledge of identities is very useful here. Like you should know that something like a plus b cube is actually the same thing as if you know Pascal's triangle. I think maybe I'll get to talk about that one day. So like binomial expansion, So if you know Pascal's triangle, so here you just know this is a cube. A will start with the highest power and B will carry 0. And B raised power 0 is simply 1. So you don't have to worry. The next thing, the power of A begins to decrease while the power of B will continue to increase. Don't forget, normally it should be A cube B raised power 0, but I didn't write that because B raised power 0 is just 1. Of course, this one has a coefficient of 3. I was going to forget that. So you have 3a squared b. And the next thing, you have 3ab squared. The power of a continues to reduce while the power of b continues to increase. And finally, you have b raised to power 3. And that is exactly what you have around here. So you have x plus delta x cubed. So you have x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. And that's taken care of. And then you have x plus delta x. We've done a lot regarding this. X plus delta x is simply x squared plus 2x delta x plus delta x squared. Of course, you have minus 4 outside. And then this remains what it is because it's not, you don't have to do any expansion. So now expansion done, and you have that taken care of at this level. Every other thing is there. So the next thing is to open things up. So you have y plus delta y. So this is x cubed 3x squared delta x, 3x squared delta x squared, delta x cubed minus 4x squared minus 8x delta x minus 4 delta x squared plus 7x plus 7 delta x minus 1. But don't forget, you have y plus delta y here. And you're at the end of the day, you're looking for delta y delta x, whose limits you find to get dy dx. So it means you have to free that left-hand side of y. So this y transfers here. So the y comes over here, as you can see, so that you have all of that expression that you had here minus y now, minus y. And don't forget that y originally is x cubed minus 4x squared plus 7x minus 1. So that's why at the end of the day, you have all this expression. You now say that's minus this value of y, which we started with. And then the next thing is when you open this up, right, you have minus x cubed plus 4x squared minus 7x plus 1. And then things become sweeter. X cubed minus x cubed will go. 4x squared minus 4x squared will go. Minus 7x plus 7x will go. Plus 1 minus 1 will go. So what do you have left? You have 3x squared delta x plus 3x delta x squared plus delta x cubed minus 8x delta x minus 4 delta x squared plus 7 delta x. So things are getting tidier, right? So now you have delta y to be equal to this. And then at this point, you can think of dividing through by delta x like we did with the original when we started the y equals f of x. So if you divide by delta x, right, you know automatically delta y delta x is equal to 3x squared. So delta x is here, it cancels out. One of this will go, so you have 1 left. One of this will go, so you have 2 left. Then this goes, you have 8x left. Delta x squared, 1 goes, you have 1 left. Delta x alone, so that goes, and you have just 7 left. So, and then you are here now. You are here now. So now that you have delta y delta x, you need dy dx. And how do you get dy dx? Dy dx is simply the limit of delta y delta x as delta x approaches 0. That means that in this whole expression now, you put delta x to be 0. So that is what that limit means. So it means you have 3x squared plus 3x. And I told you, whenever you have a limit, the first thing you do is substitute the value directly. So you have 3x squared there because there's no delta x. Then here you have 3x delta x. That's 3x times 0. Delta x squared, that's 0 squared minus 8x minus 4. Delta x is 0 plus 7. And, that way, everything that has 0 cancels out. So this goes to 0, this goes to 0, this goes to 0. And what do you have? 3x squared minus 8x plus 7, which is still that same thing you would have got if you just do it straight. 3x squared, that would just be x cubed is 3x squared, 3x squared minus 8x plus 7. So if you do that very easily, know that it wasn't usually easy from the beginning. So it came from the first principle. So if you are told to differentiate from first principle, this is how you go about it. That's really lengthy, but I mean, it's good if you know it. So let's go to trig. You've been told that when you differentiate sine x, you get cos x. But the question is how? How? So this is how we get to prove that also from, using the idea of first principle. So differentiate y equals sine x from first principle. So here we are going to have a combination of ideas from logarithm, trigonometry, and all that. So first of all, you have y equals sine x, all right? So when x increases by changes rather, if I say increase, that might be a mistake. I think it's better to use change, and because a change can be either positive or negative, that's increasing or decreasing. So a change in x delta x now will make this to become sine x plus delta x, and automatically that will affect y, and that becomes y plus delta y. And again, the next thing you do is you transfer y here. So you have delta y equals sine x plus delta x minus y. And don't forget the y originally was sine x. So you have delta y equals sine x plus delta x minus sine x. Now, see we have an issue to contend with right here. So you have sine something minus sine something. And trig has an answer for that, really. Maybe when I teach trig, you'll understand better. But there's this identity that is established in trig. It is established in trig that the sine of a particular value c minus the sine of another value d is the same thing as 2 times of the cosine of half of c plus d multiplied by sine of half of c minus d. So here now, this is like your c, x plus delta x is your c, and x is like your d. So, and that is the basis. So this one can be clearly explained when we treat trigonometry. So watch out for my videos on trig later on. Okay, so now that we have this expression, because that's the only way to go, because normally when you get here, you're just stuck, you don't know what to do again. But then your knowledge of trig should kick in here, knowing that sine x plus delta x minus sine x can be expressed as 2 cos half into, if you take x plus delta x as c, that's x plus delta x plus x, then sine half into c, that's x plus delta x minus x. That's the kind of thing we are going to do. on the next slide. So, and this is where it is coming from. So, and there we have it. We have it that now delta y, like you've seen, is 2 cos half x plus delta x plus x. That's what I just did now. Sine half x plus delta x minus x. So then you need to tidy things up. So x plus x is 2x. Then you have delta x here. X minus x. Then you have delta x left. So now things are a bit tidier than when you had sine x plus delta x minus sine x. So then you can divide by delta x now. So you have delta y delta x divided by, then equals to all this divided by delta x. And then we have to take limits, right? So you now say dy dx is limit of delta y delta x as delta x approaches 0. And this is delta y delta x now. So you have limit of delta x as delta x approaches 0 for 2 cos half 2x plus delta x sine half delta x all over delta x. Now, see what is happening here. You have half delta x up here, right? But then this one can go on its own, but then you're bringing the delta x under this for what is going to come next. So now, to tidy things up, right? This one is already settled. We don't have to add anything because you remember already yesterday we did. Sorry, I keep referring to yesterday. The last video I did on limits, I talked about the fact that the limit as x approaches 0 for sine x over x, we ended up seeing that the answer was 1. If you remember, if you check the previous video I did on limits of functions of real variables. So here now we have sine half delta x, but then that delta x is what we have down here. So if we want to take care of that, we can, we can say this is sine half delta x up there all over delta x. If you multiply delta x by 1, it is still delta x. And then you know that 1 can be anything. So 1 can be, for instance, 2 times half, 2 times half is still 1. So it's as good as you're multiplying this one by 1, if you say 2 times half. So that's why you have 2 times half delta x here to balance that out, because you need half in front of delta x to follow the same rule here, that if you find the limit as delta x tends to 0 for sine half delta x over half delta x, you still get 1. So that's why we are doing that. So now you have 2 times half delta x, which is as good as multiplying by 1. So these 2 now, can cancel these 2 in front here. You can see that. So that's why now you have this expression, limit as delta x goes to 0 for cos. The 2 and 2 have canceled out. So you have cos half into 2x plus delta x sine half delta x over half delta x. So things are looking good. And this is one function multiplied by another function. I remember one of the rules of limit is that the product of a limit is the limit of the products. So if you find the product, the limit of this product now, it is going to be limit of the first one multiplied by the limit of the second one. And for the limit of the first one, so you can substitute delta x directly. So you have delta, so put 0 for this. So you have cos half into 2x plus 0. And then we know from here that limit of sine half delta x over half delta x as delta x goes to 0 is just like limit of sine x over x as x goes to 0, which is 1. So that's why this one becomes this 1. And then this is, this is 0 now. So you have cos half 2x plus 0 is 2x times 1. So at the end of the day, you have half times 2x. That's cos x. And that is why when you differentiate sine x, you get cos x. So, and if you do the same for cos x, you get minus sine x. That's where all of that came from. So on this note, that is the end of differentiation by first principle. But then I have assignment. I have exercise you can play with on a slide far away. That's like slide 50, I believe. I think it's slide 50. Yes. So you can play with this. Differentiate the following from first principle. From what we have done so far, right? You can actually take care of ABC. You can do ABC from here, and then we'll come back later. So the first set of questions you can do from first principle. You can say I have y equals cos x there, and if you do that properly, you should get minus sine x. So if you have not subscribed to this channel, make sure you do that and press the notification bell so you can always get notified anytime I upload a new video. Thanks for listening. See you in the next video.